Well, hello friends, and Merry Christmas. Today we are going to work on the kernel heap allocator. And there is this comment in kmalloc.cpp, which has been there forever, and it says that this is a really quick and dirty malloc and free implementation just to get going. And I wrote this when I originally brought up the kernel back in the day, and I also expressed some desire for this to never be seen by people, but of course the comment is still here, so that didn't really work out. But I thought today is Christmas, so why don't we get into a Christmas mood by doing some real work towards cleaning up some of the technical debt in the kernel heap allocator and working towards actually being able to remove this comment in good conscience sometime soon. So let me give you a quick overview of the heap allocator, and then I can also tell you about some of the technical debt. And one thing, let's see where we start. I guess we can just start in kmalloc, the kmalloc function. So this is used by the entire kernel for all arbitrarily sized heap allocations. And basically we have a spin lock that we lock, and we do some stats. And then the main workhorse is this guy right here. So we call to a kmalloc global state object and ask its heap thing to allocate a size for us. And then we return that after potentially generating some profiling performance events. But yeah, so this is the workhorse right here. And just briefly, it will walk a set of heaps. So there can be more than one kmalloc heap. And these are subheaps, and we just walk the list. And the first one that is able to satisfy our allocation request gets to do so. And if we don't find a subheap that can satisfy the request, we try to expand the heap by adding another subheap. And likewise, the allocation works similarly. So we have to figure out which subheap to return that memory to. And yeah, so it's a little bit messy, because you have to walk all those heaps, but it's not the most complicated thing. And then the subheaps themselves have allocate functions and deallocate functions, of course, and then internally they are just a big byte array with a bitmap at the end that stores the allocation state of each 64-byte chunk out of that byte array. Or something like that. Numbers might be off, but yeah. And then based on the allocation request size, we either do a find first fit or find best fit search in that bitmap. So that's essentially what a subheap is here. And the big technical debt problem I want to work on today is in heap expansion. So when we don't have a subheap that can satisfy the allocation request and we have to expand by adding another subheap, the big problem that we have with that is that heap expansion has a circular dependency problem, because we add subheaps by allocating memory regions from the memory manager allocator. And that's our sort of full-blown kernel memory allocator that has VM object abstraction, manages the address space with a red-black tree for the address ranges and stuff like that. And when you call memory manager and ask it for a memory region, it will instantiate, or it may instantiate various objects that use kmalloc. So the typical example of that is the red-black tree used by the virtual range allocator. So you want to grow your kmalloc heap by adding a new subheap because you're running out of kmalloc memory, and then you call memory manager, which then tries to allocate a new virtual memory region And by doing that, it calls back into kmalloc to create a new red-black tree node. And you can imagine that some trouble could arise when you do that, right? Because kmalloc is in the middle of expansion, and then you're calling right back into it, asking for more memory. So that is sort of the main thing that I want to try to clean up today and improve. And I was thinking a little bit about how to approach this, and the solution I came up with was to simply reserve a virtual range up front. So when we boot, we will reserve a range of virtual address space for kmalloc. And then when we want to expand the heap, kmalloc can have its own internal address space allocator that uses that pre-reserved chunk, right? So basically, we would no longer need to call memory manager and ask it for address space. We just use our own internal allocator that can then be heap allocation free. So that's the basic idea. And of course, that adds a new limitation because the kmalloc heap then becomes limited by our initial virtual address space reservation. But I think that's going to be okay. We can make a reasonable reservation, and on 32-bit, it's not super great because address space is limited. We only have 1 GB total for the kernel. But on 64-bit, it's basically a non-issue. We can just allocate a huge chunk and be happy about that. And, later on, we could probably figure out different strategies for maybe making this part more dynamic, but just to get to a place where we don't have a circular dependency inside heap expansion. I just want to get to that point first, and then we can make it more sophisticated later. Because right now, the fact that kmalloc may need to call kmalloc to grow the heap is just crappy. So yeah, so let's work on that. So I think what we need to do basically is in kmalloc init, which is called at boot, we need to make a big reservation. And we can do that by calling memory manager because it will be set up at this point. Let me just double check that actually, but kmalloc init is called in the kernel init code, and memory manager init is, wait, where is memory manager init? Memory manager initialize. Memory manager initialize happens after kmalloc init. Oh, shoot. Okay, so we may need to, we probably want to do like a late init or something like that. Let's see, what does this guy do in initialize? Initialize. So it instantiates memory manager on the 0th CPU on the boot processor, and then it calls kmalloc enable expand. Aha. Right, so this is probably the place where we want to do that allocation that I just talked about for address space. So expand. Right. So at the moment, kmalloc has this concept of backup memory, which is sort of what we use when we run out of kmalloc memory. So then we switch to this backup memory while we allocate a subheap. And then I think we use the backup memory to create the subheap, and then we allocate a new chunk of backup memory for next time. It's all very rickety. So I think what we're going to do, we're just going to get rid of this backup memory concept, and enable expand is then instead going to allocate something. So kmalloc global is our global state object. Sure, that's probably fine. And it will have like, let's see, virtual, let's group this up into an object. So we'll have like an expansion data, let's call it. Expansion data, and it would have something like virtual range, kernel page directory, address space, wait, where did we get a range allocator? Here. Okay. It's been a while since I did this type of thing. So we will try to allocate some virtual range, and we need it to be, let's just start with 64 megabytes. That should hold us over for a moment. And let's make it aligned to page size, I guess. Or, we could actually go with a much chunkier alignment. Get a 1 megabyte aligned address, because then the base of this thing will be like all zeros, which will look kind of neat and recognizable. Okay, and then we will pass that in, and then maybe we'll also have like, let's make a simple bump pointer allocator for this. Next virtual address is virtual range base, something like that. Okay, and I think we can just get rid of all this old expansion logic, actually. That should be fine. In fact, what do we need in this thing even? Let's just nuke all of it. Okay, so starting over. What we want to have is a struct with our expansion data. So we can't allocate this immediately on boot, right? Because we need memory manager to be up so that we have all of the page table data structures set up. So this will be an optional expansion data. And then we can remove that m underscore here. Sure. Value base, sure. Okay, so we'll have a memory virtual range, and a virtual address. Next, virtual address. Yeah, something like that. And then it didn't like, oh, I see, because of that. Sure. That's fine. Okay, and then when we kmalloc, we don't have a heap thing here, so we'll just call some allocate function directly. And likewise, when we free something, we don't have a heap to call it on, so we'll just do that. Let me bring up the problem window here, see what we have that we have to fix. Okay. And then stats, we can just add those helpers directly. We don't have backup memory anymore, sure. Okay, so we need to implement allocate, deallocate, allocated bytes, free bytes. And then the kmalloc global heap constructor previously took in the address to the initial heap. So, oh, I forget if I mentioned that. When we boot the system, we have this piece of memory here. It's just a simple byte array of 2 megabytes that are in the kernel data segment, and we use that as the initial space for kmalloc before we have a full like page allocator. So we just use that array, and that becomes the initial subheap, basically. So we're going to keep using that, obviously, because we do need to kmalloc before memory manager is fully up and running. So I think we'll just have to, our global object thingy here will still need to have that constructor that takes a virtual address to the initial heap and a size t initial heap size. And then what are we going to do with those? I guess we're going to instantiate a subheap. So, how do we do that? So we need a separate data structure that describes a subheap. And then we can just put those in an intrusive linked list. So I call it kmalloc subheap. And it could have an intrusive list node, kmalloc subheap, and I forget all the arguments to this thing. I always forget. So it's, oh, it's just your own type. Oh, that's easy. So we'll do that. And then this guy right here can have, let's see, intrusive list of kmalloc subheap list node. And then let's see, we will have, I guess we'll just call them subheaps for now, something like that. Okay. Yeah, so we don't have to get fancy with the first implementation here. Like improving the performance of kmalloc, we can leave that to the future. Right now, we just want to make heap expansion kmalloc free. So we will start here by creating a new subheap. So where do we instantiate that? I guess the easiest thing to do is to just grab a chunk of the memory that we were just given. Let's see, how is this actually set up? Pooling. Oh, we just get a raw pointer. Okay, well, that's actually easier. So kmalloc global. Kmalloc global heap is kind of a weird name for this. Let's call it kmalloc global data. And this would be our initial heap. So something like that. And then let's chop off a page at the start, let's say. So I guess we can make a new object right there. So like this. So kmalloc subheap, and then we'll pass in initial heap plus page size. And the size, initial heap size minus page size. So we reserve the first page of a subheap. Memory chunk will be used for the kmalloc subheap data structure itself. Okay. And then let's use this guy right here, which is sort of a simple wrapper over allocate and deallocate functions. So we can instantiate this guy, this template, to still get the bitmap allocation thing that we already have. We still want that. So that would just be something like that, I guess. Yeah. Okay. And then we need a constructor. So this thing takes the memory range. Sure, that's fine. So kmalloc subheap, size t size. Yeah. Okay. And maybe we can wrap this up in a helper. So add subheap. Storage size. Okay. That seems vaguely okay. And then we needed allocate, deallocate. Deallocate. And we also need allocated bytes and free bytes. So let's just sketch these out so that we have them. And then the problem view down here can then stop showing red, which would be nice. So let's see. How do we implement allocated bytes? I guess we just walk the list of heaps. So subheap of subheaps. Allocator. Oh, okay. Allocated bytes. We just add them together. It's nice and easy. And then we do the same for the free bytes. Free bytes. There we go. Fantastic. And I guess these could be auto const. Sure. Great. And then after we add a subheap, we also want to append that to our list of subheaps, right? So subheaps, append, subheap. There we go. The alignment issue, I guess we can do that to silence the warning, or wait, no? Anyway, let's not worry too much about that right now. Okay, and then to allocate, we have to walk our list of subheaps. And then if auto putter is subheap allocator allocate size, return putter. And if that doesn't work, then let's say, then we'll try to expand add a new subheap, expand, say try expand. If that doesn't work, well, for now, let's just panic. When trying to expand kmalloc heap. Yeah, that'll be the death of us for now. But if expansion succeeds, we can simply call allocate again with the same size. Cool. And for deallocate, I guess it's again a matter of walking the subheaps and then checking if subheap allocator contains this putter. Then subheap allocator deallocate the pointer. And at that point, we should return successfully. And if we get down here, bogus pointer passed to k-free, let's say. And maybe we will also print out that pointer. But let's kernel panic on an invalid k-free. Okay, and now we are only missing try expand, which we need to come up with as well. So let's bool try expand. Okay, so how on earth does this work then? So we have a virtual range that we allocated. Where did I do that? Virtual range. Right, so we allocated 64 megabytes of virtual address space on startup. And we have the next virtual address just points to the base of that range. So I think what we're going to do, just for the simplest possible thing, just do a simple bump allocator. So we will say virtual address is expansion data next virtual address, right? New, what do we call it? New subheap base. And new subheap size will be, let's do 1 megabyte at a time. Okay. And then we also need to, next virtual address is expansion data, next virtual address offset by new subheap size. And let's see if expansion data next virtual range doesn't contain what we just came up with. I guess this would mean that we ran out of virtual address space for kmalloc. So if the new subheap base, comma, new subheap size, if that's not within our virtual range, then panic. Out of address space, expanding kmalloc heap. So this, there are graceful solutions to this, right? Like we should actually allow kmalloc to fail and return null putter, I think. But for now, let's just panic here. This isn't something that we handle gracefully today either. So dare to return a null putter and allow kmalloc to fail. The thing is that a lot of things in the kernel still don't handle kmalloc returning null putter, so we still have a bunch of work to do towards handling that well and actually checking for it. So we'll leave this fix me here. Okay, so now we have expanded. We've found a chunk of the address space that we want to use. And then we need to, or not null putter here, false. Let's say, yeah. Now we have address space. Now we need to actually get some physical memory pages and actually update the page tables so that the new address range maps to some actual physical memory. So I think we can ask the memory manager for pages. So let's ask for physical pages is dot commit. So we the only API we have for page commitment is user physical pages. We should probably have a kernel ability to commit kernel pages as well. Let's see, allocate, because there isn't such a thing as like just allocate a physical page, but there is supervisor physical pages, but they come from a special memory region it's essentially the supervisor physical page set that we have is essentially DMA compatible physical addresses. That's what that's used for. And it's a small memory reservation because not all areas of memory are compatible with direct memory access from like PCI devices and stuff like that, or ISA or whatever, like old devices. So you have to use specific ranges of memory for those. That's what this is used for, and it's a small reservation. So all other memory is currently tied up in like user physical memory in that category. So I think here we're just going to use that category here right now. And how many pages do we need? Well, we need new subheap size divided by page size. And let's see, if physical pages is error, Okay, so this is physical pages or error. Then fix me, dare to return false. Once again, if we cannot actually find the give end. Oh, we didn't. We need to update the virtual address after this, actually. Otherwise, we would potentially return false here, having already bumped the VM allocation pointer. Dare to return false. Out of physical pages when expanding kmalloc heap. Yeah. Okay. And at the end, I guess we should return true. So, okay, now we have the physical pages. Let's actually move them into a, let's just release value here. So we have them in a convenient object instead of being in an error or. So how do we do this? So now we need to actually update page tables. So, my goodness, how do we do that? We have ensure PTE to get a page table entry for a given address. And we need to hold the lock and the page directory lock when calling this, and interrupts need to be disabled. Okay, but that's fine because if we grab those locks, then that should be fine, I think. Let's see. Let's start by just grabbing those locks. So mutag, oh no, the spin lock locker. Locker, S, memory, S, lock, sure. Page directory locker, which will be for kernel page directory get lock, sure. Okay, now we are holding them locks, and then, wait, is that actually the right order of grabbing those locks? I forget. Is anybody else locking this somewhere we can look at maybe? Followed by the other guy. Okay, sure. So then we need to get the PTEs, and we want to make a loop here. So I guess we can do something like while physical pages is empty is false, then we need some kind of a iterator thingy. So new subheap base. Okay. PTE is ensure PTE. Oh, is that private API? But I want to call this from kmalloc global data. Not allowed to call that. Let's allow kmalloc global data to call this thing. Let's see. It's a little bit intrusive, right? But got to start somewhere. Ensure PTE, and then we need to what? Pass in the page directory. So kernel page directory and the vatter, and that's a private member. Oh wait, do I have to say something like that? That's a little bit awkward, but I guess it's okay. Sure. Reference to kmalloc global data is ambiguous. Oh, this is not in the kernel namespace. Shows what I know. Well, we should move it into the kernel namespace eventually, but right now let's just forward declare it outside and move forward. So, oh, dang it. I forgot to update the friend declaration. Finally. Okay. Wait, is this still not allowed? What am I doing wrong? Am I, okay. I need to colon. Okay. Thank you, finally. All right, back on track. So then what do we do with this page table entry that we have here? So we essentially want to set the physical page base to, I guess we want to grab a page. So physical pages take 1, sure. And then we take the address right here. Oh shoot, this thing returns a physical page reference counting pointer to a physical page. But at the moment, we are kind of just going to leak these guys. So let's see what we do with that. I guess we can do something like this, like leak ref, and then fix me. We currently leak physical memory when mapping it into the kmalloc heap. Yeah, that's definitely something that we could improve if we want to allow somebody to later scavenge unused pages in the kmalloc heap and like recover some of it. But at the moment, let's just like sync and leak those physical pages into the heap for now. Basically, this just means that we can't shrink the kmalloc heap as it grows. We'll leave that feature for later. The current implementation of the kmalloc heap can shrink, but all of that stuff is really rickety as well. So I think it's something that we would really benefit from starting over on anyway and coming up with a better strategy than what we currently have. So what do we do? Get. Okay, great. And I guess we can do that. Seemed to be the pattern anyway. Okay, and then we say that this is a global page because this means that a TLB flush will not actually flush mappings for this page. And the reason that makes sense is because every process on SerenityOS has the kernel address space mapped into it. And so when you're switching from process to process, you retain identical mappings for the kernel itself. And by setting the page table entry to global, that means that we can actually keep those TLB caches intact across context switches. And I think there might be some, I think there's one of those security issues from like Meltdown or Spectre or whichever it was, where that was considered to be a problem. So it's something that we might want to do differently in the future, and implement like kernel page table isolation. But I haven't looked closely at it. So for now, I'm just gonna use the global optimization like we do elsewhere in the system. And we want to say user allowed is false because these are not user space accessible memory pages. And we want to say writable, yes, the kernel heap is writable. And now we want to say present is true. Okay. And finally, we have to flush TLB for this thing. So flush TLB for we have to do like this and then the address, right? Okay. Yeah, that seems cool. And yeah, so we're taking a page and leaking it. And then when we eventually run out, I guess we could also flush everything in one go. So instead of doing one like TLB flush per loop iteration, we can also do a range TLB flush at the end. New subheap base, new subheap size. Yeah, that's slightly nicer for sure. Okay, and then this is essentially a loop variable. So maybe we should express things like this instead. Like this, and then vatter is vatter offset by 1 page size. Okay. Then we don't need this include, apparently. Try expand. So this feels vaguely reasonable. And maybe I'm forgetting something, but I think this should work, and we can probably remove a bunch of unused things here in heap.h, because the expandable heap stuff we don't need anymore. So right here, expandable heap traits, default expand heap, all of this gunk can just go away. So let's actually just nuke that, verify that it's unnecessary, that the build still works. But yeah, okay. Hey, it builds. Okay, let's see if it runs. Wait. I'm forgetting something. For sure. I never actually create the subheap, right? I just, when I expand, I just allocate memory, back it with pages, but I never actually put a subheap object in there. So I almost forgot. New subheap base as putter, new subheap size. There we go. The last step. Let's see. It would be amazing if this thing just comes up bug-free. Let's see. Oh. Oh, shit. Look at that. That's cool. New kernel heap allocator just works on the first try. Of course, we didn't rewrite the whole thing, just the expansion mechanism. The bitmap-based allocator is still there, of course. So still, it's nice when stuff starts up on the first try. Let's see if we are actually expanding, though. So I guess let's print something out here at the end, like something cool like new subheap here, size this. Yeah, something like that. Doesn't have to be fancy. Just want to see that we are actually creating new subheaps. And I imagine that we create one probably right away when we boot up, but or I mean, not right when we boot up, but sometime during the boot, like, because we have a whole bunch of things happening. Ah, look, new subheaps right here, and there's another one right here, and another one right here. So we create a bunch of them, and if we open up the memory stats here, we can see the kernel heap is 4.1 megabytes. So I guess that adds up. We have the 2 megabyte initial pool, and then we add on top of that 3 heaps, 1 megabyte each, and we are just 100K into the third one. So it all checks out. Very, very cool. So let's do something like run test.js or whatever, just to verify that things don't fall apart. Okay, you can see that it's creating new heaps here. And then again here, which is a little bit concerning because I would imagine, I would hope that since the process exits, it would free up everything that was being used. So if we keep expanding the kmalloc heap, that's probably indicative of some kind of a leak somewhere. So that's probably something we should fix, but that's outside the scope of what we're doing today. But I really dig this, actually. So let's say that, what if we have like a really small VM allocation? So instead of 64 megabytes, we would have an additional, I don't know, like we would only have 6 megabytes, right? And then we would start a bunch of programs and verify that things fall apart. So let's just double check that. Test.js, sure. Start some random things. Oh, we already died, and it says out of address space when expanding kmalloc heap. So that's fine. That is fine. So 64 megabytes is, it's very little, obviously on 64-bit, but it's easy to increase this number on 64-bit. We can increase it substantially. On 32-bit, it's harder because we only have 1 gigabyte total kernel memory to play around with. So because of that, 64 megs is already, it's already 6.25% of our total VM range that we have to play with. But yeah, so fix me, this range can be much bigger on 64-bit, but we need to figure something out for 32-bit. But I don't know, maybe the solution here is that over time, we kind of work towards not even having the 32-bit version of the kernel. I don't know. There are a lot of things that are nice about 64-bit that are annoying about 32-bit. Many of them address space related, right? So it's possible that the solution for this whole issue is to simply get rid of 32-bit. But this isn't the time or place to, or it's not the time to make that kind of decision. It might be the place, but not the time. So we'll leave that one on the thinker for now. But yeah, so I think this is really, really cool. And let's add also a double check that we don't call kmalloc while we are expanding our heap. So let's see, kmalloc global. This whole file is kind of messy. We could probably like move things into the kmalloc global object and so on. But I think I want to work on this a bit more and like move things around, and then we can figure out like what's a good abstraction for everything. But we can definitely have like just a simple Boolean that's something like in expansion in progress, let's say. And we'll do something like this here. So temporary change, expansion in progress is true while we are in try expand. And then we simply, not here, we verify here that expansion in progress is false if you try to allocate or deallocate, or actually if you try to expand. So we don't want to expand the heap while expanding it. And I think that's a very reasonable guard to have so that we don't have those types of problems anymore. All right, so I feel quite good about these changes, and obviously it's going to require more than this to be able to actually remove that comment about the kmalloc heap, because we still have really bad performance issues. We have some fragmentation issues, and now we've added some new issues as well. We are trading in, we're fixing some large technical debt and adding some small technical debt, but these new issues are easier to fix, like the statically sized address range and the lack of heap shrinking. So as you can see here, the heap usage has shrunk down to 4.2 megabytes out of 8.8 megabytes total. I don't know why that's being rounded like that. It should probably say 9 megabytes, but I don't know why that happens. Anyway. Oh, actually, I guess we are using a page where when you create a heap, we are using the first page for the subheap object, but I think also the heap template thingy here puts the bitmap that tracks the allocation state of each chunk. It puts that in a chunk, in like a blob at the end of the provided memory range. Let's see how that happens. So bitmap is memory plus total chunks. Yeah, right. So it puts the bitmap at the end, and it ends up that you actually don't get, if you allocate 1 megabyte of physical memory, what you end up with is not 1 megabyte of available kmalloc heap, but rather the metadata takes up some of it. That's why we don't get a perfectly round number. But the thing I was trying to say, actually, when I got distracted by the rounding, was that, as you can see, we've shrunk down the amount of memory in use, but we didn't shrink down the total memory. And that's something we could definitely improve upon. And of course, it's still the case that if you had just one allocation remaining anywhere in one of those subheaps, you wouldn't be able to free that entire subheap. So fragmentation can still prevent heap shrinkage, and there are different solutions to that. Like you can use smaller subheaps, or you can have different allocation strategies and so on. But I guess I'm pretty happy with this progress. So let's see if we can turn this into a commit. And let's also get rid of that message here. We don't need that. And adding a subheap can't fail, right? Yeah. So by the way, let's look at why this is allocation free, because I think the reason that the old one was not allocation free was because it does stuff willy-nilly, like appending things to vectors and using the red-black tree in the address range allocator and so on. But the reason that this is allocation free is because we make that range allocation upfront. So that will, of course, do an allocation, but it happens up front. So it comes out of that initial pool right here. It will allocate out of that red-black tree, but just the one time. And then when we do our expansion, the reason that expansion is allocation free now, or kmalloc allocation free, is that all that we really do is try to commit physical pages, which we've already done a bunch of work on to make allocation free. It's just updating counters and using the physical buddy page allocator thing that doesn't use the heap. And then when we create the subheap object, we instantiate that object within that memory range that we just picked up physical backing for. So that goes into that thing itself. And, there's an argument against inline metadata that we could look at later. and maybe separating out the metadata for better security and stability properties. But at least it doesn't use any kmalloc for that. And then appending to the list of subheaps is using intrusive lists. So there's no additional allocation required to append to subheaps because it uses pointers within the subheaps themselves. And actually, now that I think about it, maybe unsure PTE, this guy might actually allocate somewhere. I don't know that for sure. Yeah, so it does have a problem actually that it will sort of lazily add page table data structures to the kernel page directory. So this could actually fail internally, and then it will return null putter. And that would happen if you're out of physical memory. Even if you had just enough physical memory so that you could satisfy the subheap, but then you try to allocate a physical page for the now newly allocated address range. We need to create like a page directory entry and a page table for that, and we don't have backing. This will fail. So this was actually not the right thing to do. We should do this and then do this. Panic. This is kind of gnarly, but and we're definitely gonna have a fix me about that. So what we would really need is a way to ensure up front before getting into this loop here that we have enough page table pages. I guess one thing we could do is we could do sort of a dry run of this range and just call ensure PTE on every address just to make sure that all the page tables are in place. And then once all that is done, then we go through it again and actually populate those guys. But I'm going to leave that as an exercise for our future selves because I don't know exactly how to do that in a nice way. Out of, let's see, unable to acquire PTE during heap expansion. Yeah. Fix me. And if ensure PTE fails due to lazy page directory construction, it returns null putter and we are in trouble. Find a way to avoid getting into that situation. And perhaps we could do a dry run through the address range and ensure PTE for each virtual address to ensure that each PTE is available. Not maximally efficient, but could work. Needs more thought. Yeah, it needs more thought. Yes. Okay, great. So let's commit. Getting rid of the old and in with the new and the simpler. Very much like that. Wait, what actually changed there? Oh, I just changed the name of the thing. Right. Okay, so how do we describe this? Kernel. Simplify, make kmalloc heap expansion kmalloc free. That sounds really strange, but previously the heap expansion logic could end up calling kmalloc recursively, which was quite messy and hard to reason about. This patch redesigns heap expansion so that it's kmalloc free. We make a single virtual range allocation at startup. When expanding, we bump allocate VM from that region. And when expanding, we populate page tables ourselves instead of going via memory manager. Directly ourselves. Yes. This, let's see. This removes a large amount of overly complex. Let's not shit on the old code actually, because it got us to where we are today. I don't like to crap on old code. I think that's kind of unproductive, so let's not do that. But this makes heap expansion a great deal simpler. However, do note that it introduces two new flaws that we'll need to deal with eventually. The single virtual range allocation is limited to 64 megabytes, and once exhausted, kmalloc will fail. Actually, it will panic for now. And the kmalloc heap can no longer shrink once expanded. Subheaps are stay in place once constructed. This is a regression from the well, yeah. Let's not overthink that, but yes, as mentioned here, like these are new flaws that we need to deal with eventually. So yes, I think this turned out pretty good. And let's see if there's something that we can get rid of from the header. Kmalloc impl. That doesn't seem to exist anywhere. Enable expand. That's kind of a strange name for that function. Okay, yeah, that's kind of an uninteresting little detail there, but you know, let's update the copyright headers actually while we're here. I didn't actually touch that file, I just removed stuff, so let's not be overly zealous, but let's do this. Well, now I'm also just removing stuff. Yeah, let's cool it on that one, but see, kernel, remove unused function prototype for kmalloc impl declaration. Okay. Yeah, so this comment is still true, I think. It's still quick and dirty, but it is, in my mind, improving a little bit now, and we will keep improving upon this going forward. But this will be it for today's video. So if you made it this far, then I thank you for watching and for hanging out. I hope that you saw something interesting here, and I look forward to doing more work on kmalloc and showing you more of that work in the next video. So thank you very much, and I will see you all next time. Bye.